It's a great pleasure to present again our R package one step in the user conference. I am Alexandre Brousse, professor in statistics at Le Mans University, and it's a joint work with Christophe Dutemps. In some regular cases, the maximum likelihood estimator shows consistency and asymptotical efficiency. But in general, this MLE has no closed form and must be computed by a numerical optimization method which is time-consuming for large samples. The one-step estimation procedure is a fast alternative which is also asymptotically efficient. Up to now, the one-step package allows the user to compute the estimator for observation samples composed of RID random variables. Loading the proper library, we can perform, let's say on a simulated sample of RID gamma variables, for which we forgot the shape and rate parameters, the one-step estimator with the one-step command. It has been shown in our last paper that this procedure is faster than a MLE for a similar asymptotic efficiency. We want to extend the one-step estimation procedure to counting processes, especially to inhomogeneous Poisson processes appearing in numerous applications like biology, physics, finance, and others. Let us consider such a counting process N with a deterministic intensity function, denoted lambda, parameterized by an unknown parameter theta. This function gives the probability to have a new event around time t. The most simple example is maybe the Poisson process, for which the intensity is constant over time. And we talk about inhomogeneous Poisson process when it changes with respect to time. Here, there are two examples simulated by the thinning method. It can be remarked that there is more events counted when the intensity is large and less when the intensity is small. There are two kinds of statistical experiments explained on the corresponding poster. First, the observation of single process where the horizon time tends to infinity. And that won't be described in this presentation. And second, the observation of several independent paths on a fixed interval of time. In this second setting, the likelihood can be expressed with the intensity function. The MLE is asymptotically efficient, but it is generally not explicit and time-consuming for large samples. Consequently, a one-step approach can be proposed. Let us describe again the one-step procedure in this setting. We start from an initial moment estimator, denoted theta type, which is fast to be computed, but which is not asymptotically variance efficient. In the one-step procedure, the initial estimator is corrected by a single step of the gradient descent method on the log likelihood function. Here, the Fisher information, I theta, described in the poster, can be evaluated by numerical integration. The one-step PP function that will be available in the next version of the one-step package allows to estimate the parameters of a general specified intensity function. As an example, let us consider a parametric intensity function which is gamma distributed, for which scale and shape parameters have to be estimated. In this example, we can see on the histogram of statistical errors for the shape parameter, done with Monte Carlo simulation, that the maximum likelihood estimator is asymptotically efficient, with the optimal limit distribution in red, but that it is time-consuming. On the other hand, the moment estimator is explicit in this example and fast to be computed, but it is not asymptotically variance efficient, with the blue limit on the histogram. But by a single step correction, the one-step estimator is asymptotically efficient and can be computed 10 times faster than the MLE. Thank you for your attention. Please feel free to ask your question at the following address.